Welcome back to the course. So, till now we have seen how we can set the constant in the that means in the DC environment, how we can load the libraries, how we can read the HDL file. So, ultimately after doing all these things, we have to compile the things for translating from expression to the corresponding gate level representation, right. So, that is the job of the compilation, or I can say that is the job of the synthesis. So, during the compilation we follow several optimization techniques. So, optimization that can be in the architectural optimization or optimization in terms of area, power and speed. So, optimization to achieve the specification. So, optimization can be done in several ways, like architectural optimization we have seen in the last class. So, now we will see the logic level optimization. So, okay. So, the logic level optimization we can do, that means, which is basically, as I said, that optimization works on, that means whenever we read the Verilog file, it has been initially converted into the generic technology library of Synopsys. Then after on that particular that means file, now each of these optimization technique will be applied. So, one of the technique is structuring. So, this process basically adds intermediate variables and logic structure to a design, which can result in reduced design area. And structuring is constant based. It is based applied to non-critical timing paths. So, that means structuring is one of the optimization technique which is applied to the design, which is already, that means, converted into the GTEC netlist file. So, based on that we are applying this structuring. Structuring basically it puts intermediate variables and logic structure, and it is not at all basically applied on the critical paths. It applied only non-critical timing paths. Okay. So, this is one of the structuring is one of the optimization technique for logic optimization. Another technique of logic optimization is flattening. So, flattening I think we have already discussed earlier, but again flattening is the goal, or the flattening is the process which basically converts the combinational logic paths of the design to a low level sum of product representation. That means it basically tries to collapse or tries to reduce the number of levels which are present in the hierarchy design. So, that is why flattening is carried out independently of constant. It is useful for speed optimization because it leads to just two levels of combinational logic. During flattening, design compiler removes all intermediate variables and therefore all its associated logic structure from a design. That means flattening means that is somewhat related to ungrouping. So, ungrouping, by ungrouping of the levels of hierarchy, what we do. So, by flattening we basically do all that thing. So, that is why by this structuring and this flattening we can avail the, that means logic level optimization. So, after logic level optimization, what is there? That is gate level optimization. So, gate level optimization works on the generic netlist file, again on the GTEC, that means netlist file created by a logic synthesis to produce a technology specific netlist file. So, it includes the following processes, which is one of that is mapping. So, mapping means this process uses gates from the target library to generate a gate level implementation of the design, whose goal is to meet timing and area goals. You can use the various option of the compile ultra or compile command to control the mapping algorithms used by design compiler. For more information, see sequential mapping. So, what is mapping basically? Mapping means now the generic netlist file is already there. Okay. So, now I will try to convert, or I will try to that netlist file, now it will be mapped to the target technology file. So, that means the basic gates or the basic components which are available in the target library, now that will be used in to represent or to implement my function or my expression, right. So, whenever we are doing that, at that time we have to meet the goal of speed, power as well as area. So, whenever we are basically how this DC expert and DC ultra, they are different. basically their optimization algorithm is different. Whenever we are selecting these two, that okay, with the compile mode should be in the higher, that means on the higher side, that means we are running on the compile ultra, advanced features should be included. So at that time that means the algorithm complexity increases, or which basically optimize the circuit in a better way rather than the basic mode. Okay. So then the delay optimization, this process goal is to fix delay violations introduced in the mapping phase. So delay optimization does not fix design rule violations or meet area constant. For more information, see delay optimization. So design rule fixing means the DS, that means whether there is any that means floor planning violation or any, that means size violation, something like this. The design rule violation, if it is there, that also you have to check. So this process goal is to correct design rule violation by inserting buffers or resizing existing cells. So design compiler tries to fix this violation without affecting timing and area results, but if necessary, it does violate the optimization constant. Then area optimization, the process goal is to meet area constant after the mapping, delay optimization and design rule fixing phase are completed. However, design compiler does not allow area recovery to introduce design rule or delay or constant violation as a means of meeting the area constant. Okay. So that means all these phase, delay optimization, design rule fixing or area optimization, this is run one by one. So first the mapping process starts. After the mapping process, this delay optimization it happens. So after delay optimization, then this design rule fixing has been happened. Then after all these things happen, this area optimization that is happened. Okay. So this is the optimization flow. First it do the automatic area ungrouping, then high level optimization and data path optimization, then multiplexer optimization and mapping, then sequential mapping, then Boolean optimization and mapping, then auto unification, then implement synthetic parts, timing driven and power driven combinational optimization. Then register retiming means if it is necessary, then it will happen, otherwise it won't. And then delay and leakage optimization, then design rule fixing, then area optimization or area recovery. So now what are these steps? Basically what are the, that means what are the job of this, each of these steps? This is the full optimization flow which happens in DC, so or design compiler during the compilation mode. Okay. So what are the job of each of these layers, that we will discuss now. So in the automating, the first actually of this is automatic ungrouping. So the compile ultra command automatically ungroups all logic hierarchies. Ungrouping merges subdesign of a given level of hierarchy into parent cell or design. It removes hierarchical boundaries and allows design compiler to improve timing by reducing the levels of logic and to improve areas by sharing the logics. So automatic ungrouping means if I chose this compile ultra, so at that time this automatic ungrouping happens automatically, that is the ungrouping happens automatically to make one single file which consists of all the submodules. So then the next phase is that, but in the basic DC mode it does not happen, it is not automatic. If you select, if you tell the tool to do this or ungrouping, then only, that means that is manual. If you tell the tool to do the ungrouping, at that time it will happen, otherwise it won't happen. So high level optimization and data path optimization, then it is the next phase of optimization process. So during the high level optimization, resources are allocated and shared. Depending on timing and area consideration, resource sharing enables the tool to build one hardware component for multiple operations, which typically reduces the hardware required to implement your design. Additionally, optimization such as arithmetic operation and sharing of common sub-expression are also performed. And each of these, if it is required, then only it will be performed, otherwise it won't. When it will be performed, if my specification is too much that means stringent, that means I am not, that means I have put like my actual requirement, the first phase of that means synthesis process, if the requirement says that okay, actual requirement is 20 nanosecond, but my budget is 10 nanosecond only, that means specification or the constant is 10 nanosecond. So at that time it will try several ways of like this putting this arithmetic optimization or this resource sharing or this say common sub expression sharing. These techniques it will allows to meet this timing or this area requirement, right. So this is the actually job of this that means high level optimization or data path optimization. Then the next is this multiplexer mapping and optimization. Okay. So multiplexer mapping and optimization, in this phase design compiler maps combinational logic representation multiplexer in HDL code directly to a single multiplexer or a tree of multiplexer cell from the target logic library. So design compiler reorders select signal for better area and CS multiplexer trees. So that means now this using multiplexer we can represent any combinational circuit, right. So now using marks that means whenever this multiplexer mapping and optimization happens, then several that means blocks that may will be implemented or tries to implement it with the help of multiplexer, okay, and DC automatically do that. Then this sequential mapping, what is sequential mapping? So sequential mapping phase consists of two steps. First, it registers the register inferencing by HDL compiler, and then technology mapping by design compiler. So that means sequential mapping has two phases. So this HDL compiler do the register inferencing, that means it infer the registers, and then technology mapping by the design compiler. Technology mapping to a technology library. So the RTL is translated into technology in independent representation called as sequence gen. The sequence gen is then mapped to gates from the logic library. So a sequence gen is a generic sequential element that is used by Synopsys tool to represent registers and latches in a design. Sequence gens are created during elaboration and are mapped to flip-flops or latches during compile. So that means this, what is this mapping? So that means actually now why I am telling that okay, this in the starting phase this is by basically done this is implemented using Synopsys. Registers are basically implemented through sequence gen, or this other combinatorial logic is being implemented by GTech library. But whenever we will see the tool, at that time it will be much more clear or much more visible to you that okay, so whatever I am telling now, that is happening there, okay. So the next phase of this optimization process is structuring and mapping. So once it has been converted into the generic technology library file, so after that we have to now you have to translate again to the corresponding technology library file. So in this phase, in the structuring and mapping phase, what it does, the tool optimizes the unmapped unstructured logic and maps it to technology gates, that means using the technology library. So structuring is one of the option, and then flattening is another option. We have already discussed this. So after that, automatic unification, okay. So unification. So what is that unification? The unify process copies and renames any multiply reference design so that each instance reference is unique in a design, okay. So suppose cell U1 I have that means copies 10 times in my design. So every time this U1 will be named as U1 _ 1, U1 _ 2. Actually that may be different, but it will be unique by its name. The process removes the original design from the memory after it creates the new unique design. So the original design and any collection that contain it or its objects are no longer accessible. The tool automatically unifies design as a part of the compile process, okay. So that also you will see how it happens. So implementing the synthetic part. So synthetic part means, so as I said that okay, so only I have assigned the multiplier as like star or this plus operation, okay. So the HDL operators are basically associated or the known as the synthetic part, which are bound in turn to synthetic modules. So each of these synthetic modules can have multiple architectural realization called implementation. Like what I said, that multiplier, that can be that you can use any that means architectural techniques you can use, like Baffuli multiplier you can use, this Wallace 3 multiplier you can use, or that Booth's multiplier you can use, or any generic multiplier structure you can use, Vedic multiplier structure you can use. So there are several structure or several ways of implementation for single particular operator multiplier. Okay. So but now here what we are doing, we are just putting, okay, I need a multiplier, I don't want to design it, so I just need it from the library. So for at that time what will happen, so if I just mention that as a star, so automatically that star indicates what is the, based on the specification, that what is the length, what is input and output length, or the, that means word length of that, based on that will be inferred from the corresponding design by library. And that now that from that library is basically having one particular architecture, okay, because it is fully optimized based on a particular architecture. Okay. So now that architecture, now that will be converted during the compile process, now that will be converted using the corresponding target libraries basic gates. Okay. So this is the, that means job of the implementing the synthetic part. So after that what we have to do, we have to, that means the optimization flows passes through the timing driven combinational optimization. So here that means the timing that means known as, okay, that is one of the that means primary concern. So at that time, based on that logic optimization or any other combinational optimization that performs. Okay. So during this phase the DC performs optimization in the combinational path. So this phase has two components, timing driven structuring or incremental implementation selection. So during timing driven structuring, the tool restructure the logic in the critical path. So I said one of that means the operators reordering is maybe one of this technique to do this combinational optimization. So then another this during the incremental implementation selection, the tool explores alternative implementation for each synthetic operators, and it evaluates, replaces the synthetic implementation along with the critical path to improve the delay cost. Okay. So that means obviously it will, for one particular that means operator, though there are several structures, so it will obviously based on the timing information requirement, it will try to select the appropriate structure which is basically follows the corresponding timing budgeting. So then this register retiming, I said that, okay, register retiming is a process where whenever we are having that means we are not putting any extra register to the circuit, just by reordering the registers in keeping the functionality same, we can improve the performance, that means speed performance of the system. So that thing is only available in DC Ultra, not in other mode it is not available. So whenever the speed, that means timing constant is not matching, so at that time we can put on, or we can just go through, or we can try out, or we can opt for that particular option. So then design compiler provides the following ways to perform register retiming. When you can perform the register retiming, or design compiler include the register retiming options. So when the optimized registers command performs the register retiming of sequential element for pipeline design. The compile ultra command supports the retiming option, which enables design compiler to automatically perform local retimings moves to improve host negative slacks. So what is slack, what is this multi-cycle path, what is false path, that we will see in next few slides in the timing analysis part. So this capability called adaptive retiming, optimize and interdesign, it works best with general non-pipeline logic. So pipeline is another logic. In pipeline what we do, we basically put extra register to the circuit. So but in retiming we don't put any extra register. So this timing the pipeline circuit, if there is any extra register which we can put that means we can, that means put in critical path to reduce the critical path. So by balancing that, we can, one thing is that means we have to keep the functionality same. So by doing that, we can do that, this register retiming. So then the next path is this delay and leakage optimization. What I said, that if I said that okay, this leakage optimization is true or this power optimization is true, at that time only this option will be enabled, otherwise this is not. So in this phase, what design compiler do, it fixes the existing delay violations by traversing the critical path. During the delay optimization, DC re-evaluates existing implementation to determine if they meets the constant. So basically, based on the frequency only, frequency information only, we can calculate the dynamic power, because it is proportionate to the operating frequency of the circuit. So that's why once it reduces the delay, that means reduces, or it calculating the delay, that means this total, that means timing information or the operating frequency information. After that, it starts calculating the that means power consumption, and then it tries its way like clock gating technique or any other technique for reducing the power optimization, that means power consumption. After that, what is there, that means that we have to fix the design rule, that means we have to check whether all the, that means height, width of the cells and geometric description all are okay for the design. That we have to see, design rule fixing we have to done. Okay, so that will be done, that means in design compiler for fixing those design rule. So after the design rule fixing, that means delay optimization has been done, sequential mapping has been done. So after each and every part it has been completed, so we have to go for the area optimization. So that means area, delay and power, that has been done optimization. So now we can go for the area optimization. So during the area optimization, the DC attempts to minimize the number of gates in the design without degrading the delay cost. That means the delay will not be touched or the power will not be touched, but it will try to reduce the area by reducing the number of, that means this logical optimization, logic level optimization or gate level optimization. So in DC Ultra, you can use this compile underscore ultra and optimize underscore netlist hyphen area commands to provide significant area improvements. That means here manually I am insisting the tool to do the that means optimize the netlist in terms of area, that you also can do. Okay. So and then this to optimize the netlist area command performs the monotonic gate to gate optimization to improve area without degrading the timing or leakage. You can use the optimize netlist area command as the final area recovery step at the end of the synthesis flow. You can also use the command to legacy netlists. Okay. So this is that means this is the total flow which basically one by one completed in the synthesis part. So optimization technique for best and worst case condition. Okay, so best and worst case condition means actually whenever we are designing a chip, so at that time the typical case is the normal condition, but in some case it may happen that the temperature is increased, okay, or temperature is decreased. So I have to check, or I have to check the performance of my system in the best possible case of the that means all this process voltage temperature, as well as the worst possible case of process voltage temperature. So that's why there are three type of library. One vendor provides three type of library. One is done for that means typical case, which is for the normal case, and best case is for that means the where everything is on the higher side, and worst case for the where everything is on the lower side. Okay. So you see the first whenever you are that means using one or multiple libraries, the general methodologies which has been followed if you in the optimization technique, that is that best and worst case operating condition based on this library information, then optimistic and pessimistic while load models, that means while load models is also supported by provided by the technology library vendor, then minimum and maximum timing delays, This is also based on the timing information provided by the library. So, if you see multiple libraries, see optimizing with multiple libraries. So, at that time what you have to do, specify minimum and maximum constant like environmental, which includes the operating condition and while loads, clock information, which includes the clock skew and clock transition, optimization, which includes the input output delays, drive strength, loads, that means capacitive loads and the resistance, the design rules, which includes the transition time, fan out as well as the capacitance. Okay. So, this optimization technique, it optimizes the design for simultaneously for minimum and maximum timing. That means for both the things we have to check. So, whenever we are checking the timing, at that time what type of violation we can come, that means you can get, that is setup time violation or hold time violation. Okay. So, what is setup time violation, what is hold time violation? If you are getting setup time violation, if you are getting hold time violation, how to remove this violation and why they are coming, that we will see in the static timing analysis chapter. But all these things, whenever we will do the timing analysis, at that time using prime time, at that time prime time is one of the tool which is basically used for static timing analysis. So, we will use that tool. So, there we will, in DC also you can calculate, okay, but in timing analysis, in prime time you can calculate it more properly. Okay. So, after that, after doing all these things, report and analyze all the paths showing the constant violation. The following constant related reporting and back annotation comments support both minimum and maximum optimization and timing analysis. That means, after doing all this violation, after getting all these violation, now you have to fix all these violation and get the corresponding the final, that means netlist file of your design by using design compiler. So, for today this is it. We will cover the next things, or that means which is not covered yet in the next future slide or future lecture.